Hello science fans. Today, we're going on an amazing journey to explore a very special group of elements. Imagine a group of celebrities who are so cool, they don't need to interact with anyone else to be famous. In the world of chemistry, these are the noble gases. You can find them all lined up in the very last column on the right side of the periodic table, a special place known as Group 18. This family includes 6 members: helium, neon, argon, krypton, xenon, and the slightly infamous radon. They are truly the aristocrats of the elemental world, standing apart from all the others with their unique and fascinating properties. So, what makes these gases so noble or special? Well, for starters, they are completely invisible to our senses. They are colorless, meaning you can't see them. They are odorless, so you can't smell them. And they are tasteless, so you can't taste them. They are the ultimate masters of disguise, existing all around us without making a fuss. This quiet nature is a huge clue to their chemical personality. Unlike other elements that are eager to hook up and form molecules, the noble gases prefer to remain single and independent, floating around on their own. This characteristic is what scientists call being inert, which is just a fancy way of saying they are not very reactive. Their inertness is the key to their power and their many uses in our daily lives. Think about it. If you need an element that won't interfere with a delicate process, a noble gas is your best friend. This unreactive nature stems from their atomic structure. All atoms have shells of electrons, and the noble gases have a full outer shell. This is like having a complete collection of your favorite trading cards. You don't need any more, and you don't want to give any away. This full shell makes them incredibly stable and content, which is why they rarely form chemical bonds with other elements. They are perfectly happy just the way they are, which makes them both predictable and incredibly useful. This family of elements, despite being all around us, is actually quite rare in the grand scheme of things. While argon makes up about 1% of the air we breathe, the others are present in much smaller amounts. They are extracted from the air through a process called fractional distillation, where air is cooled until it becomes a liquid, and then slowly warmed up to separate each gas. From the party balloons floating at a birthday celebration to the bright signs that light up our cities at night, these silent, invisible gases are working behind the scenes, making our world a more vibrant, advanced, and safer place. Let's dive in and get to know each member of this exclusive club. Let's start with the smallest and most famous noble gas, helium. When you think of helium, you probably picture colorful balloons floating high up to the ceiling, or maybe you even remember the funny, high-pitched voice it gives you if you inhale a little bit. That's because helium is much lighter than air, about 7 times lighter in fact. This property makes it fantastic for lifting things, not just party balloons but also giant weather balloons that carry scientific instruments into the upper atmosphere and even massive blimps that drift gracefully through the sky. It's the second most abundant element in the entire universe, created in the fiery hearts of stars, but here on Earth, it's a bit harder to find. But helium's talents go far beyond making things float. One of its most critical jobs is in the world of cryogenics, which is the science of very, very cold temperatures. Helium has the lowest boiling point of any element, meaning it can stay a liquid at incredibly cold temperatures, close to absolute zero. This makes it the perfect coolant for the powerful superconducting magnets used in MRI machines in hospitals. These machines help doctors see inside the human body, without surgery, and they couldn't work without helium keeping their magnets super chilled. So in a way, helium is a true lifesaver, playing a silent but vital role in modern medicine. Because helium is so stable and non-reactive, it's also a fantastic protector. In high-tech manufacturing, like making semiconductors for our computers and smartphones, or in specialized welding, it's crucial to keep oxygen away. Oxygen can cause metals to rust, or ruin delicate electronic components. By pumping a space full of helium, workers can create an inert atmosphere where these sensitive tasks can be performed safely. Even deep-sea divers rely on helium. They breathe a special mixture of helium and oxygen called heliox to prevent a dangerous condition called nitrogen narcosis, or the bends, when they dive to extreme depths. Helium's story is one of incredible usefulness, but it also comes with a word of caution. The helium we use on Earth is a finite resource, trapped underground in natural gas deposits and formed over millions of years from the radioactive decay of elements. We are using it up much faster than it can be replenished, leading to concerns about a global helium shortage. This means we have to be smarter about how we use and recycle this precious element. While it's fun for balloons, its roles in science, medicine, and technology are simply too important to waste. Understanding helium helps us appreciate this amazing lightweight powerhouse. When the sun goes down, our cities come alive with a dazzling display of lights, and for that, we can thank another noble gas, neon. When you pass an electric current through a glass tube filled with neon gas, it glows with a brilliant, unmistakable reddish-orange light. This is the magic behind the iconic neon signs that have decorated diners, theaters, and cityscapes for over a century. The word neon itself has become synonymous with this type of lighting, but here's a fun fact. Not all colorful signs are made with pure neon. To create different colors, sign makers use other noble gases or colored glass tubes. For example, argon gives off a pale blue or lavender light. Speaking of argon, it's the quiet workhorse of the noble gas family, and the most abundant one in our atmosphere. While neon grabs all the attention with its bright personality, argon is busy with many important behind-the-scenes jobs. One of its most common uses is inside traditional incandescent light bulbs. The tiny metal filament inside a light bulb gets incredibly hot to produce light, and if it were surrounded by oxygen, it would burn out in an instant. Argon creates a protective, inert environment that allows the filament to glow for hundreds of hours without breaking down. It's a simple, clever solution that makes our homes brighter. Argon's protective qualities also make it a star player in insulation. If you have modern, energy-efficient windows in your home, chances are there's argon gas sealed between the panes of glass. Because argon is denser than air, it's not as good at transferring heat. This means it helps keep your house warmer in the winter and cooler in the summer by creating an invisible thermal barrier. This reduces the need for heating and air conditioning, which saves energy and helps protect our environment. It's an amazing example of how an unseen gas can make our homes more comfortable and sustainable. Both neon and argon are essential in fields beyond lighting and insulation. Argon is widely used in the welding industry to shield the hot metal from the air, ensuring a strong, clean weld. In the food industry, it's used to displace oxygen in packages of snacks like potato chips, keeping them fresh and crispy for longer. Neon, meanwhile, is used in devices like high-voltage indicators and certain types of lasers. Together, these two gases show us how the noble gas family contributes to our world in both dazzlingly obvious and quietly essential ways, from the brightest signs to the very air in our windows. Now let's move down the periodic table to the heavier, rarer, and more exotic noble gases, krypton and xenon. These elements are far less common than argon or neon, making them more expensive, but their unique properties make them indispensable for some very advanced applications. Krypton, for instance, is known for producing a very bright, whitish light when electrified. This makes it perfect for high-performance lighting, like the powerful landing lights on airport runways that need to cut through thick fog, and in certain types of photographic flashes that require an intense burst of light. It's like a supercharged version of the gas in a regular light bulb. Krypton also plays a critical role in modern medicine, particularly in laser technology. Some of the most precise lasers used for eye surgery, such as LASIK procedures that correct vision, use a mixture of gases that includes krypton. Its ability to help generate a specific wavelength of light allows surgeons to reshape the cornea with incredible accuracy. Furthermore, just like argon, krypton is an excellent insulator. In fact, it's even better than argon at stopping heat transfer, so it's used in the highest-end, super-insulated windows. While its cost limits its use to specialized situations, krypton proves that sometimes the rarest elements are the most powerful. Then we have xenon, the true heavyweight champion of the stable noble gases. Xenon is incredibly dense and emits a brilliant, intense blue-white light that is very similar to natural daylight. This is why it's used in the high-intensity discharge headlights found on many modern cars, which illuminate the road far more effectively than traditional halogen bulbs. Xenon is also used in the powerful lamps for movie projectors, filling the giant screen with a bright, clear picture. Its ability to produce such intense light makes it a star in the world of high-performance illumination, turning darkness into day. But perhaps xenon's most futuristic application is in space travel. Many satellites and deep space probes are equipped with ion thrusters, a highly efficient form of propulsion. These engines work by shooting out ions, electrically charged atoms at very high speeds to generate a gentle but continuous push. Xenon is the perfect fuel for these thrusters because its atoms are heavy, so they provide a good amount of push, and it's chemically inert, so it won't react with the engine components. Thanks to xenon, spacecraft can travel farther into our solar system than ever before, all while using very little fuel. Xenon is truly helping us reach for the stars. At the very bottom of the noble gas column on the periodic table, we find an element that is very different from its relatives, radon. While the other noble gases are known for their stability, radon is famous for being radioactive. This means its atoms are unstable and naturally break down, or decay, over time. As they decay, they release tiny particles and bursts of energy. Radon is formed from the natural radioactive decay of uranium, an element that is found in small amounts in soil, rocks, and water all over the world. Because radon is a gas, it can easily seep out of the ground and into the air we breathe. And because it's radioactive, radon poses a unique set of challenges and health risks that we don't see with the other noble gases. Since it can emerge from the ground, it can accumulate inside buildings, especially in basements and lower levels that have less ventilation. Outside, radon disperses quickly and is harmless, but when it's trapped indoors, its concentration can build up to dangerous levels. When people breathe in radon gas over a long period, the tiny radioactive particles it releases can damage the cells lining the lungs. This damage can lead to lung cancer, and in fact, radon is the second leading cause of lung cancer after smoking. This risk means it's very important for people to be aware of radon levels in their homes. Since radon is colorless and odorless, the only way to know if you have a problem is to test for it. Simple and inexpensive test kits are available that can measure the concentration of radon in the air. If high levels are found, there are effective mitigation systems that can be installed. These systems typically work like a vacuum, using pipes and a fan to draw the radon gas from beneath the house and vent it safely outside before it has a chance to enter the living space. It's a serious issue, but one that can be managed with knowledge and action. Despite its dangerous reputation, radon has had some limited uses, particularly in medicine. In the past, it was sometimes used in a type of radiation therapy to treat cancer, where its decaying atoms could be directed to destroy tumor cells. However, due to the risks involved and the development of safer alternatives, this use has become very rare. Today, radon is primarily an element of concern, a natural environmental hazard that we must monitor and control. Its story serves as a powerful reminder that even within a family of elements as stable as the noble gases, there can be a rebellious member with a powerful and potentially dangerous nature. The story of the noble gases is a fantastic scientific detective story that unfolded in the late 19th century. For a long time, chemists thought they had a pretty good handle on the composition of the air we breathe, believing it was mostly nitrogen and oxygen, with a few other trace components. However, a British scientist named Lord Rayleigh noticed something peculiar. He found that nitrogen extracted from the air was slightly denser than nitrogen produced from chemical reactions in the lab. This tiny difference suggested that there was something else hiding in the air, an unknown, heavier gas mixed in with the nitrogen. Intrigued by this puzzle, Lord Rayleigh teamed up with a brilliant Scottish chemist named Sir William Ramsay. Together they embarked on a mission to isolate this mysterious substance. In 1894 they conducted a clever experiment where they removed all the known gases, oxygen, carbon dioxide, and nitrogen, from a sample of air. After all that was gone, a small bubble of gas remained that refused to react with anything. They had discovered a new element. They named it argon, from the Greek word argos, which means lazy or inactive. A perfect name for an element that wouldn't react with anything. This was the first noble gas to be identified. Ramsay was convinced that argon was not alone, and that it was part of a whole new group of elements on the periodic table. His hunt continued. In 1895 he learned that a gas was released when a certain mineral was heated. He collected this gas and analyzed it, finding that it was helium, an element that had previously only been detected in the spectrum of the sun's light. The discovery of helium on Earth confirmed Ramsey's theory that there was an entire family of inert gases waiting to be found. He realized that the best place to look for the rest of them was right where he found argon in the air. Using the new technology of cooling air into a liquid, Ramsey and his colleague Morris Travers painstakingly separated the different components. By carefully boiling off the liquid air one fraction at a time, they discovered not one, not two, but three new elements in 1898. They named them neon, meaning new, krypton, meaning hidden, and xenon, meaning stranger. It was an incredible series of discoveries in a very short time. For his monumental work in identifying an entire group of elements, Sir William Ramsey was awarded the Nobel Prize in Chemistry in 1904. His curiosity and persistence revealed a hidden layer of our world, the silent but powerful noble gases. So, what is the secret behind the noble gases' aloof and unreactive behavior? The answer lies deep inside their atoms, in the arrangement of their electrons. As you may know, atoms are made of a central nucleus surrounded by electrons that orbit in different energy levels, or shells. The electrons in the outermost shell are called valence electrons, and they are the key players in chemical reactions. Most elements have incomplete outer shells, which makes them unstable. They are constantly trying to achieve a full outer shell by either giving away, taking, or sharing electrons with other atoms. This electron swapping is what we call a chemical bond. The noble gases, however, are different. They are the cool kids who already have everything they need. Every member of the noble gas family, with the exception of helium, which is full with just 2, has 8 electrons in its outer shell. This octet, or set of 8, is an incredibly stable arrangement. An atom with a full outer shell is like a completed puzzle. It's perfectly balanced and has no desire to change. There's no energetic advantage for a noble gas to lose an electron, gain an electron, or share its electrons with another atom. They are electronically content, which is why they are so chemically inert. This stability is why they exist in nature as single atoms, a property known as being monatomic. While oxygen in the air we breathe travels in pairs, and water is a trio of atoms, noble gas atoms like helium, neon, and argon fly solo. They just don't need to form bonds to be stable. For a very long time, scientists believed that it was impossible to make noble gases react with anything. They were even called inert gases for this reason. It seemed like a fundamental rule of chemistry that these elements would forever stand apart from the rest of the periodic table. However, science is all about challenging what we think we know. In 1962, a chemist named Neil Bartlett managed to do the impossible. He created the first ever compound of a noble gas by reacting xenon with a highly reactive fluorine compound. This groundbreaking discovery showed that under the right, extreme conditions, even the noble gases could be forced to react. Since then, scientists have created several other compounds of xenon and krypton. This doesn't change the fact that they are incredibly stable, but it did force chemists to change their name from inert gases to noble gases, acknowledging that while they are very reserved, they are not completely unreactive. While the noble gases are generally considered environmentally friendly because they are non-toxic and non-reactive, their use and supply chain present some important challenges we need to consider. The biggest concern revolves around helium. As we've discussed, helium is a non-renewable resource on Earth. It is created by the slow radioactive decay of uranium and thorium deep within the Earth's crust and gets trapped in the same underground pockets as natural gas. When we extract natural gas, we can separate the helium. However, once helium is released into the atmosphere, say from a popped balloon, it's so light that it eventually escapes Earth's gravity and is lost to space forever. This leaking into space means we are depleting our finite global supply of helium at an alarming rate. This has led to several periods of helium shortages and price spikes, which impacts more than just the party supply industry. Scientists who rely on liquid helium for their cryogenic research and hospitals that need it for their MRI machines face significant challenges when the supply is tight and the cost is high. This has pushed industries to develop better helium recycling and conservation methods. For example, modern MRI machines are being designed with systems that can re-liquefy the helium gas as it boils off, ensuring none of it is wasted. On the other end of the spectrum, we have the environmental issue posed by radon. Unlike the supply problem of helium, the issue with radon is its presence, not its absence. As a naturally occurring radioactive gas, radon can seep into homes from the ground and pose a serious health risk. It is a silent and invisible threat that requires public awareness and proactive testing. Governments and health organizations run campaigns to educate homeowners about the dangers of radon and the importance of testing their homes. Managing this natural hazard is a key part of ensuring public health and safety in many regions around the world. For the other noble gases like neon, argon, krypton, and xenon, the main environmental consideration is the energy required to produce them. These gases are extracted from the air through cryogenic fractional distillation, a process that involves cooling huge volumes of air to extremely low temperatures. This process is very energy-intensive, which means it has a carbon footprint associated with the electricity used to power the separation plants. As our use of these gases in technology and industry grows, it becomes increasingly important to make the extraction process as efficient as possible, and to recycle these gases whenever feasible to minimize the overall environmental impact. As we've seen, the noble gases are far more than just a quirky, inactive group of elements at the edge of the periodic table. They are silent but mighty powerhouses that have fundamentally shaped our technology, our science, and our daily lives. From the helium that lifts balloons and cools vital medical equipment, to the neon that illuminates our cities, and the xenon that propels spacecraft to distant worlds, these elements are unsung heroes. Their unique property of being chemically stable makes them the perfect candidates for jobs where reliability and non-interference are paramount. They are the ultimate protectors, insulators, and illuminators. The importance of studying noble gases continues to grow as we push the boundaries of science and technology. Researchers are constantly finding new and innovative applications for them. For example, xenon is being explored for use in advanced medical imaging and as a potential treatment for brain injuries due to its anesthetic and neuroprotective properties. In the world of computing, noble gases are crucial for manufacturing the complex microchips that power our digital world, and they may even play a role in the development of quantum computers. Their predictable nature makes them invaluable tools in the most cutting-edge research fields. Looking to the future, the responsible management of these resources will be more critical than ever. The challenge of a finite helium supply requires us to think like planetary stewards, prioritizing its use for essential scientific and medical applications, and investing heavily in recycling technologies. Similarly, continued public education about the risks of radon is essential for protecting community health. As our demand for high-tech devices and advanced manufacturing processes grows, so too will our need for argon, krypton, and xenon, making efficient extraction and recycling practices an economic and environmental necessity. In conclusion, the noble gases are a perfect example of how even the most seemingly simple and unremarkable substances can hold incredible power and potential. Their discovery was a triumph of scientific curiosity, and their applications have revolutionized countless industries. By continuing to study these stable, silent elements, we not only deepen our understanding of the fundamental laws of chemistry, but also unlock new tools to build a brighter, healthier, and more advanced future. The story of the noble gases teaches us a valuable lesson. Sometimes, the greatest strength lies not in being reactive, but in being perfectly, powerfully stable.